An example. Sketch the region consisting of points satisfying 0 less than or equal to phi, less than or equal to pi fourths, and 0 less than or equal to rho, less than or equal to 2. Also express this region in terms of cylindrical coordinates. Now, suppose we didn't have that last statement, and we just said 0 is less than or equal to phi, less than or equal to pi fourths, and 0 is less than or equal to rho, less than or equal to 2. Would we know which coordinate system we're in, and how? We're in spherical because we see rho and phi. So rho and phi are tied to the spherical coordinate system. Okay, so now we know we're in the spherical coordinate system. And what we have is we have two constraints. One constraint says that phi is going to be between 0 and pi fourths. So let's talk about that constraint for a while. Do you remember where phi equals 0 is? So if I'm in my three-dimensional space, and I know you're thinking, hey, that looks like you're trying to do Cartesian coordinates, but here it's just saying this is my space. I'm just trying to sort of cement our space. Do you remember where phi equals 0 would be? Z-axis, and in particular this positive z-axis. So this is your phi equals 0, straight up. And what happens is, as you come off the phi axis, as you come off the z-axis, you increase phi. So by the time we hit the xy plane, we would have gone to pi halves. Well, that's too far. We're going to go halfway in between. So pi fourths is a cone. So phi equals pi fourths is a cone where every angle for the points, so regardless of what point, if I come over here and I pick this point, and I say, well, what's the angle there? It's pi fourths. If I pick a different point on the cone, it's still pi fourths. Doesn't matter. Any point I pick on that cone, the angle's always pi fourths. So that is the right cone. All right, well, if I say phi is between 0 and pi fourths, what are my points? Well, there's a lot of them. In particular, it's everything that's inside this cone, including, going up. So that's what those points are. Everything inside the cone. So that's the first constraint. So now let's talk about our second constraint. So here we have that rho goes between 0 and 2. Okay, rho is distance from the origin. So rho equals 0. What would that be? It'd be the origin, because you haven't moved out from the origin. Rho equals 2 would be what? It'd be a sphere. Can you tell me about the sphere? For example, what's the radius? If rho equals 2, the radius of the sphere would be 2. Because rho measures how far out you go. So if I want to have all the points where 0 is less than or equal to rho, less than or equal to 2, what am I including? What are my points that I want to include? Yeah, everything that's inside the sphere. So my points that satisfy 0 less than or equal to rho, less than or equal to 2 is that sphere. Now, what do we want? Well, we want the points which satisfy both. That's the word and. You need to satisfy both. So what do? Well, you get one of those fancy 3D things where you cross your eyes and say, okay, what satisfies both? So when we do that, you don't have to do our fancy 3D thing, but these images combined, what do we see? Well, what's going to be on the quote-unquote bottom? It's going to be the cone. The cone is going to be what's on the bottom. What's going to be on the, again, quote-unquote top? The sphere. So what's going to happen is it's going to be coming up as the cone until you hit a certain point where the cone and the sphere happen to intersect. And then you're going to be topped off by a portion of the sphere. So what kind of shape is this? I mean, if you were to describe it to your family, going home, kind of like, yeah, it's kind of like an ice cream cone. And you know, you're at that key part where, I don't know how you consume ice cream cones, but you know, civilized people, you know, they like to sort of gently lick the ice cream, and they're at that key moment where it's just right. You're just about to start nibbling into the cone. All right, so that's the sketch. All right, so we finished the sketch. Now there's a second part. Express the region in terms of cylindrical coordinates. Now when we think of cylindrical coordinates, I really like to think in terms of what can I say about what's happening in the z direction, or if you want to sound very British, you can say the z direction. So we've already used the term top and bottom. So let's think about this in terms of cylindrical. The bottom is the cone. Well, what is the cone in cylindrical coordinates? What does this translate into, this cone? Do you remember? Yeah, this translates into z equals r. In general, a cone is z equals some multiple of r. If z equals a large multiple of r, then what happens is you have a very tall, very skinny cone. If z equals a small multiple of r, you have a very broad, very low cone. So different cones for different purposes. If you were making, say, a wizarding hat, you'd probably want a large value of r. If your pet had recently gone to the vet, you'd want a small value of r. You know, it just depends what you need. Okay, so in particular, we can say, look, we got to be above that, so z has to be at least as big as whatever r is. So that's a constraint. So that's from the cone. How about the top? Well, the top is a little bit more subtle, but let's think about it. So it's a sphere of radius 2. X squared plus y squared plus z squared equals 4. Okay, that's the shell. So that's in Cartesian because we're comfortable with Cartesian. X squared plus y squared, if I switch to cylindrical, what does that become? R squared. R squared plus z squared equals 4. Now I can solve for z because I really want to try to describe things in terms of z. So z squared is 4 minus r squared. And once I have that, if I solve for z one more step, I get z equals plus or minus square root of 4 minus r squared. Well, what does the plus or minus come in? I mean, what does the plus represent? Yes, the top half, and the minus is the bottom half. And you might say, it seems like we're missing variables, but remember, there's no theta here, so theta can be arbitrary. So this is getting back into that spinning action. It doesn't matter what our value is because we can spin theta around, so it sweeps everything out. So if I want to be below this top part, what needs to be true about my z? Less than or equal to that positive part, 4 minus r squared. And now, those two completely describe my region. So I can combine them together into a single stretch of inequalities. R is less than or equal to z, less than or equal to the square root of 4 minus r squared. And that's our way to describe the region in cylindrical coordinates. All right. Now on to our next topic. For our next topic, we're going to keep going and understanding things. And where are we at? Well, we've talked about coordinate systems. We've also talked about distance. And so the next thing we need to talk about is change. In other words, I want to say, how do points compare? That's really what I'm after. I have a set of points, and I want to know, how did I change to go from one location to another location? And what we need to do is we need to have something which includes both direction, because change happens in a certain direction, and magnitude. Magnitude, we could say, is an amount. Usually we think of it as a length. So how are we going to do this? And the answer is, we're going to do vectors. So when we talk about vectors here, vectors are the thing which we're going to use which have both these things. They have a direction and they have a magnitude. Now, how do we think about them visually? Well, we think of them as directed line segments, or if you like, arrows. So I have various vectors. So I can think about my change is going from the end of the arrow to this, well, I shouldn't call it the end, the start of the arrow to the end of the arrow, or the tail to the head. So the change is how much happened, the difference between the start and the end. Now, vectors are not tied to a specific location. So in other words, if I have a vector, if I pick it up and I move it, it's still the same vector. So it's not that that vector says it has to be at this point. No, a vector is movable. What a vector is just saying, how do things compare? So here we have a collection of vectors drawn visually. Are any of these vectors the same? So to be the same, you have to check two things. Do they have the same direction? And do they have the same magnitude? And if you can say yes to both, they're the same. And it turns out that there are two which have the same direction and the same magnitude. Now, if you were patient, you might say, wait, these two vectors have the same direction. Are they the same vector? No, because their magnitudes differ. And then this vector actually has the same magnitude as those two. Are they the same? No. Direction differs. So you have to check both. Now, between direction and magnitude, what's more important? Well, it usually depends on the application. We're going to spend a lot of time talking about direction, because that tends to be the thing which takes a little bit more time to build up that intuition. Now, once you have an object, you want to say, well, what are things we can do with this object? So what are some things we can do with vectors? Well, one thing we can do is we can change the length. So, for instance, we said, look, this vector has the same direction, but the wrong magnitude. Well, I can change the magnitude by an operation called scaling. So scaling says, look, just make a vector a different length. So there's a couple things that happen. If I'm scaling by a positive number, what will happen is I'll just keep the same direction and just modify the length. So if I have a vector v, twice v, same direction, twice as much change. Half v, same direction, half as much change. But I can multiply by any number. So I can multiply by a negative. If I multiply by a negative, the effect is to reverse. So when I have negative, you'll notice that my arrow now goes on the opposite end, because I've reversed. So we want to be careful here. Now, one of the things that we're going to talk about are vectors which are parallel. What does it mean to be parallel? It means that they differ by a constant. You can think of parallel as being the same direction, but you have to put direction in quotes, because of course there's this notion, well, v and negative v aren't really the same direction because they're pointing opposite of each other, but it's exactly opposite, so they are parallel to each other. Okay, so that's scaling. We can scale vectors. What else can we do? Well, we can add vectors. And here, to say add is we're combining vectors together. So we have multiple vectors, and we put them together. And the way we put them together is think about what are they representing. They're representing change. So if I have vectors and I want to put them together, I want to add them, I'm trying to ask the question, what's the net change? And the way I do it is I say, well, combine their changes. So, for instance, I can think about my vectors, and here's an illustration here where I have vectors u and v. You'll notice I actually have u and v in multiple places. So if I want to know what happens when I combine u and v, well, I say, first, start with u, go to the end, and then, once you reach the end, apply v. So it's like we put them one right after the other. And so the result is a new start and a new end. That new vector, that's u plus v. Now, does it matter whether I do u first and v, or v then u? And the answer is no. It doesn't matter. You get the same answer. So in other words, it doesn't matter what order you add vectors. You'll always get the same answer. All right. Are any questions about vectors? We will be answering many of them.
What about subtraction?
Well,
Like, does order matter in subtraction?
well, order matters in subtraction in as much as it matters. I mean, how do you subtract? You subtract is add a negative. That's how you subtract. So if you can scale by a negative and you can do addition, you can do subtraction. Well, one of the challenges we have is that it's really great and intuitive to think of vectors in this way. These arrows, it's beautiful pictures, but we're number people. We're calculus. We want numbers, things we can manipulate. Well, how do we get there? So the way we're going to do it is we're going to introduce a couple of special vectors. So there's 3 special vectors in 3 dimensions, and we're going to spend most of our time in this class in dimension 3. And we're going to explain why dimension 3 is such a cool dimension next week. It turns out there's a really cool fact about dimension 3. But you'll have to wait until next Friday to hear that. So we're going to have 3 special vectors. We're going to call them I, j, and k. So what is I? Well, I is the vector that points in the x direction, in particular the positive x direction. But there's one other thing. We want to make sure it's not just any vector in the positive x direction, length 1. So I, if we come down here to our axis, would be right there. I'm moving in the positive x direction, length 1. J moves in the y direction, positive y, length 1. And k moves in the positive z direction. So there's my I, j, and k. Now, how do we use these 3? Turns out there's a lovely fact. And here it is. Every vector in 3 dimensions is a combination. And they use the phrase linear combination of I, j, k. Now, if the phrase linear is making you nervous, linear is just a fancy way of saying I'm scaling and I'm adding. So it just says you multiply these I, j, and k's by appropriate constants and add them all up. That's what we mean by linear combination. Anytime you hear the word linear, just think I can scale and add. So how do we see this? So to see this, I'm going to draw a vector here, and I've already drawn it ahead of time, anticipating that this would come up. So here I have 2 points, point A and point B, and I have a vector that goes from A to B, which is often denoted by saying AB with an arrow over it. See, the arrow indicates the direction. I'm going from A to B. And I say, well, what am I doing? What I can do now is I can think about this box. There's this box set up here. And I can say, how can I get from A to B by using the box? Well, what I can do is I can move along the edges. So for instance, I can move first along an edge. So this bottom left, and then I'll move along the bottom here in the front, and then I'll move up. And if I move along those 3 edges, you'll notice, where do I start? I start at A, and where do I end? I end at B. So these 3 vectors combined together are the same as AB. So if I can find out what these 3 vectors are here, and I add those together, then I'll be good. Well, let's think about the first vector. What direction is it pointing? It's pointing the x direction. In fact, you'll see it's parallel to I. So if it's parallel to the vector I, that means it's a multiple of I. Well, now we just have to figure out what multiple it is. Well, how much did my x change? I started at x1, I ended at x2, so how much did I change? x2 minus x1. So this first vector is x2 minus x1 times I. Because it's the amount of change in that direction times a vector that points in that direction. What about the second vector? Which direction am I going? Well, I was hoping someone would ask or say why, and say, well, because we need to know. And you're like, no, that's a Calc 2 joke. Come on. We're better than that. All right. It's a change in the y. And so if we're changing the y, we're moving in the j direction. So this vector is a multiple of j. Which multiple of j is it? Yeah, it's y2 minus 1. It's how much you've changed in the j direction. So y2 minus y1 times j. The last one, by process of elimination, which direction? It's in the z direction. It's a multiple of k. Well, what vector is it? z2 minus z1 times k. And so, now we have our really nice basic fact. This vector AB is x2 minus x1 times I plus y2 minus y1 times j plus z2 minus z1 times k. So in other words, I just add those three vectors together. Lo and behold, I start and stop at the same point. So I'm the same vector. And life is good. And now what we do is, oh, there's a typo there. That one should be a subscript. Now we'll fix it in post-production. All right. So now what we do is we say, look, we're going to just treat these numbers in front of I, j, and k as like numbers. So I'm just going to grab what's in front of I goes in my first slot, what's in front of j goes in my second slot, and what's in front of k goes in my third slot. And what we're going to do is we're going to call this my vector. So here, I've turned my vector now into a triple, where the first part of my triple, that's my change in x. How much did x change? The second part is my change in y. How much did y change? And the third part is my change in z. So the vector here is recording my change. How much am I changing? Okay, so this is called component form. So component form gets us back into our nice, comfortable thing. It says, hey, think of vectors now as a set of three numbers. Numbers? We love numbers. Now we can do computation. Woo! All right. Word of warning. It kind of vaguely looks like a point, because the notation for points is similar. But what's different? Well, notice that for a point, we use these round symbols. We call them parentheses. But for vectors, we use these pointy symbols. They are called angled brackets. And, okay, so what's the point? They're not the same thing. A point refers to a particular position in space. A vector talks about a change. Now that being said, we're going to have a lecture coming up in about a week where we do a very fancy thing where we change our round parentheses for points to pointy vector things. But be careful, don't confuse them. They're different types of objects, and so they don't behave the same way. All right, time for an example. Find the vector which goes from some point and goes to some point. So, but I haven't filled the points in, so you get to pick the points. All right, what should our first point be? 4, 2, 5. 420 is my office number. You can, great place if you're looking for me. Okay, and goes to where? 7, 6, -9. All right, got to get some negatives in there. Look, I know we're optimistic people, but we got to recognize that some people look at the world negatively. All right. So how do we do it? Well, what is the vector doing? It's telling us to change. So, if I'm going from 4, 2, 5, which is here, and I'm going to 7, 6, negative 9, which is here, now you're probably thinking, wow, that was fast. The reason I was able to do it fast is I didn't care. Because look, the picture is just to get the intuition. Don't worry about correctness. Usually 95% or more of the time, you just need the intuition. Okay, but the point is I have the point 425, and I'm going to the point 7, 6, negative 9. So the intuition says, all right, let me think about what's happening. The vector in component form is going to say, look at the change. Now, the question is, what do I do? Is it the 4 minus the 7, or is it the 7 minus the 4? It's the 7 minus the 4. You take where you end and subtract where you start. So 7 minus 4 was 3. Okay, next, we ended at 6. We started at 2, so our change was 4. All right, we ended at negative 9. We started at 5. Negative 14. A lot of change there. All right. And we're done. Okay, so once you have points, it's easy to find the vector between them. But it's also easy to do other things. So for instance, if I say, I have a point and I have a vector, if I start from that point and go in that vector, I want to know where I end up. Again, it's just understanding, okay, the vector is my change. Apply the change to see where my new point is. So these are things we can do. All right. Well, now that we have our component form, what is it good for? One thing it's good for is it gives us a really easy way to do things we've already talked about. So we talked about scaling and we talked about adding. And so for component form, if I want to scale and add, then I can do it by doing entry-wise. So to scale is to multiply by a constant. So I multiply my vector by some constant k. So here is k a, b, c. And what do? Well, that's k times a, k times b, k times c. I scale in each direction. Intuitively, this makes sense because if I think about what happens, if I'm scaling, it's I'm multiplying my change by a certain amount, by k. So I'd multiply my change in each direction. So I'd multiply the change in the x, it would be k times as large. My change in the y, k times as large. And change in z would be, again, k times as large. If I want to add, well, if I have two vectors, a, b, c, and d, e, f, I just add entry by entry. So I combine the changes in x, the changes in y, and the changes in z. All right. So scaling and adding, very easy for component. You just do the intuitive thing. Think intuitively, and you're probably going to be okay. We'll break you about thinking intuitively next week. But for now, think intuitively. Okay. What about length? That was magnitude. How do you find that? Well, to do that, we think geometrically. Okay, what is the length? Well, it's the amount we've changed. So if I have a vector a, b, c, one thing I can do is I can say, well, let me just put that vector so it starts at the origin. Because again, vectors can be put anywhere. Why not just put it so that the tail is at the origin? We can do that. And then the vector comes out. Where would the vector a, b, c end up? What point would I be at? So if I'm at the vector, if I am the vector a, b, c, and I put it so the vector starts at the origin, where's the end point? It's at a, b, c. So now if I want to know the length of the vector, I just say, well, what's the difference? Or sorry, what's the distance between a, b, c and 0, 0, 0? So I apply the distance formula. It's the square root of the a minus 0 squared, b minus 0 squared, c minus 0 squared, all added up. All right. So now you can find the magnitude of vectors very easily. Okay. So this is pretty good. The component form is working out very nicely with us. There's another notational note which says, hey, we're using the same type of symbols that we've seen before. We're using these bars here. We've seen bars like this. That's absolute value. Now, did we do that because we ran out of symbols and so we started recycling? That does happen in mathematics, by the way. Or did we do that intentionally? And in this case, this is an intentional thing. Whenever you see that sort of notation where you see this, what looks like absolute values, you should think of it, oh, this is measuring size. Because that's what absolute value does. If you think about a number, what does the absolute value of a number measure? It's the size of the number. So if I talk about the absolute value of 3, it's 3 because the size of it is 3. Absolute value of negative 3 is what? It's still 3 because that's the size. Here, size is how far you are from 0. That's what absolute value is measuring. So that's one thing to be aware of. It's really nice. It sort of says, oh, all these things fit together. There's a consistency going on. Another thing to note is that different books use different notation. Some books will use 2 bars instead of 1 bar when talking about magnitude of vectors. So just be aware. Unfortunately, there has not been a universal agreement on notation. So even if you pick up a few calculus textbooks, odds are pretty good they'll disagree on a half dozen notational things. They always agree on the important parts, like that arctangent, it's an awesome function. But notational parts they sometimes disagree on. An important vector that we're going to see often is the unit vector. Now, what does unit mean? When you see the word unit, you should think of 1. Like a unit circle, circle of radius 1. A unicycle, it's a one wheel. A unibrow, just one brow. A unicorn, a single corn. So whenever you see the word unit, you think 1. So a unit vector, okay, it's a vector which has length 1. So what's special then? See, if we already know the vector has length 1, magnitude is no longer important because I know that the magnitude is automatically 1. But what 2 things does a vector have? Magnitude and direction. So that says the only thing important about a unit vector is the direction. So that's why it's important to work with these. So we're going to use these to work with direction. Now there is one vector out there. It's called the 0 vector. And we denote it with the 0 with an arrow. And what's the 0 vector? Well, it's the vector which has no change. So all the entries, component-wise, are 0. Now the 0 vector has no direction. I like to think of it, it's the art history major of vectors. No direction. None. All right. So we will work with the 0 vector from time to time. Mostly it's just, watch out. Make sure you know what you're working with. Now, it turns out that as long as you have a vector and it's not the 0 vector, you can change the magnitude. Well, we can always change the magnitude. But the important thing is I can make the magnitude just right. And by just right, it says I can scale it to make it a unit vector. And so, as a result, I can always find a unit vector that points in the direction of any given vector I want. So we're going to do some examples. So find some unit vectors with the same direction as the following vectors. Now you'll notice I didn't write anything down, but that's because we'll write some stuff down to start with. Okay, I'll do the first one. Suppose my vector here is 6, 8. Now you might notice one thing right away. What dimension am I in? I'm in 2. So far, I really have limited my discussion to 3 because 3 is really awesome. Again, we'll talk about it next Friday. But everything we've talked about works for any dimension. Most of the time we'll be in 2 and 3 because those are things we can draw. But we can always talk about higher dimensions as well. We will not. Okay, 6, 8. So this is my current vector. All right, we'll call it u. All right. Well, first thing, is this a unit vector? Probably not, because those are big numbers. Generally speaking, a unit vector can't have a number bigger than 1, because you can never have any entry bigger than 1. All right. Well, what's the current magnitude of this vector? Well, square root of 36, 6 squared, and 64. 36 plus 64 combined together to give me 100. Square root of 100? 10. All right, we were right. It's not a unit vector. Okay, so how much do I have to scale by to get to a unit? 1/10. 1 over the magnitude. So 1/10, 6, 8 is a unit vector. Can we leave it like this? Yes. But we could also say this is 6 over 10, 8 over 10. By multiplying the 1/10 through. And remember, you multiply it through to each entry. What's another way to say 6 over 10? 3 over 5. 8 over 10? 4 over 5. 4/5. Okay. All right, so that was the first one. Let's go to 3 dimensions. Okay. So, your turn. Give me some numbers here. Preferably not huge. 7, 2, 3. All right, again, I'll throw in a negative. Just, vectors can have negative numbers. That's perfectly allowed. They don't always have to be in the third entry. Okay, so what do we do next? Magnitude. Okay. Now, what do you get? Well, square root of 49 plus 4 plus 9. If I add those all up, I get the square root of 62. And the square root of 62 is, of course, still square root of 62. Really close to the square root of 64. Oh, well. So what do? 1 over the magnitude, square root of 62, times the vector 7, 2, negative 3. In this case, I would say it's not worth the effort to put it in. Because the 1/10, if we put it in, we could actually get some cancellation, some simplification. Here we wouldn't. So I'd say, okay, leave it as is. That's fine. That's fine. Let's do one other thing. Suppose I had the following. Suppose I said W is sine t, cosine t, t. Where right now I'm just saying t is something. Now you might say, am I allowed to do that? So I'll ask you, am I allowed to do that? Sine t, cosine t, t. What's the answer? Yes. Yeah, it's fine. It depends on what t is, but that's perfectly fine. It's just, right now you should think of a vector as a collection of changes. Changes are something. So what's the magnitude of W? What do? So you apply the magnitude formula. It's the square root of, what's first? Sine squared, and then cosine squared, and then t squared. Can you simplify that? Yeah, sine squared plus cosine squared. Nice fact. That's 1. So square root of 1 plus t squared. And so, if I want a unit vector, I could take 1 over the square root of 1 plus t squared, just barely making it there, times sine t, cosine t, t. And that's perfectly fine. And you're probably thinking, would we ever do that? Yes. Oh my gosh, you've already learned. Foreshadowing of things to come. Okay. All right. Well, I worry there's not going to be any surprises left. Okay. Well, a few more things to go through. First, some notes. Vectors work fairly intuitively. Now, what do I mean by that? It's sort of like what you expect to be true is true. So let's just sort of check our intuition. If I have a vector u, and I add the 0 vector, what will I have? I'll still be u. Nothing has changed. If I have the vector u, and I add the number 0, what do I have? I have nonsense. Why? Well, the problem is these are two different types of objects. One's a vector, one's a number. You can't mix. This is, people might say oil and water. But look, you have to be careful. Make sure that what you're doing makes sense. You have to mix things that are, all right, that's the only nonsense one, by the way. No more nonsense. Okay. If I have a vector u and I scale it by 0, what do I have? The 0 vector. Not just a 0 number, 0 vector. Okay, if I have a vector u and I scale it by 1, what do I have? I still have u. If I have u and I subtract u, what do I get? 0 or 0 vector? 0 vector. Okay, if I have a plus b, and those are numbers, and I multiply by the way, I hope you can see that there's a consistency here. Whenever I put a vector, there's like a little arrow over the top of it. Okay, so a plus b, those are scalars, times by u. What can I do? AU plus BU. In other words, it's like we can multiply this through because we can multiply it through. What if I have A, which is a scalar, times U and V added together? What can I do? I can again distribute. AU plus AV. And last thing, if I have the magnitude of A times the vector U. So A is a number, U is a vector. What can I do? So, let me say, is this correct, where I pull out an A? And why is it not correct? Because A could be negative. So how do we fix it so it's correct? You leave it with absolute value. So this goes back to, like, if you remember when you did numbers, absolute value of AB is the same as the absolute value of A times the absolute value of B. So it's the same thing. There's some consistency going on. Now, midpoints. So if I have 2 points, the midpoint is the point which is halfway in between. In fact, if you think about the word midpoint, it's like it's in the middle, the point in the middle. It's like we almost want you to understand these words. We've had a lot of time to think about what to say. So what's the idea? I have a point here, and over here I have another point. So here's x1, y1, z1. Here's x2, y2, z2. And I want the point halfway in between, in the middle, this point right here. And how do I find it? Well, it looks like what we did is we added the points together and divided by 2. For example, x1 plus x2 over 2. That's the x-coordinate. Can we do that? Can you add points together and divide by 2? No. You can't add points because there's nothing geometrical. Points are not things you can combine together. So how do we justify it? Well, what are things we have available to us? We have vectors. So what you can do is you can say, well, look, here's a vector that goes from x1 to x2. It's not very bright vector, but you can see it. And I can say, look, this vector is what? It's x2 minus x1, y2 minus y1, z2 minus z1. That's a vector. Now, I want a vector that doesn't go the whole length. I want a vector that goes half the length. How do I find a vector that goes half the length? I scale it. By how much? Yeah, I take this and multiply it by half. And now I say, look, I have a vector that goes half the length. Start at x1, y1, z1, go half the distance, and we're at the midpoint. So by using vectors, we're allowed to carry this out. Okay, do an example here. Find the midpoint between some points. Okay, some more points. All right, give me some points. -5. 12. 4. And? -2. -2. 0. -9. All right. So what's the midpoint? Well, you add the x coordinates and divide by 2. So it's like halfway in between the x coordinates. So negative 5 plus negative 2 divided by 2, negative 7 over 2. 12 plus 0 divided by 2 would be 6. 4 plus negative 9 divided by 2 would be negative 5 halves. Okay, so we can find midpoints. And we have a couple minutes left, so we can finish our last example. So suppose you have a parallelogram. Now the word parallelogram has a lot of L's. And you'll notice that these L's are parallel to each other. And hence, what's happening is you have sides which are parallel to each other. So I have this A, B, C, D. These are the vertices of a parallelogram. And the sides are parallel. And what we want to show is the following. If I look at A to C, and I look at B to D, and I look at where they intersect, the claim is that they intersect at the midpoints. Okay, so how can we argue this is true? In the interest of time, I'm going to speed up a little bit. Let's introduce today's topic, vectors. Let's call this vector u. What's this vector over here? It's still u, because it's parallel. It's the same vector. I've just translated it. That doesn't change anything. What's this vector? Well, new vector, we'll call it v. And I know I'm forgetting my little arrows. Okay, and this one? Still v. Now, this vector that goes from A to C would be u plus v. So, if I wanted to get to the midpoint, I'd start at A, and I'd go halfway. So from A, to get to the midpoint between A and C, I take half of u plus v. Now, this one will have, this is a thinker here. What's this vector? So I'm going from B to D. Thinking, processing. Do you have an answer?
Negative something?
It's going to be u minus v. Now, if you want to figure out why, just think about the effect. If I go v and then I go that vector, it's the same as u. So v plus whatever this is better be u. So it should be u minus v. Now, what do I get? Well, I go v to get to b, and then I add half of u minus v, and lo and behold, that's how I get to the other midpoint. Now, what's true about these two things? They're the same, and therefore the midpoints are the same. And time is up, and start again next time.